Okay, let's get going. First things first, is anybody still not signed up in ISIS? If you're not signed up in ISIS, you should probably see me and we'll try to figure out what's going on. At this point, most everybody should be in the system. And so what I'll start doing is that when we finish grading homework 1, I will put homework grades on Trunk, the Trunk website, and I've never actually used it, so this will be a learning adventure for me too. But we will try to do that and see how it works. Have you used Trunk before in other classes? Does it work all right for grades? OK, we'll go with it and see what happens. For those watching the videos, probably not you in here because you're here, but for those watching the videos, I am struggling with trying to get the board and the PowerPoint slides to show at the same time. Like one's either too bright or the other's too dark or whatever. So I may have to play around with the background colors in the slides. So I apologize. The slides themselves are on the website. So better to see the board in class than the slides. Yes, Ben?
Would it work if you shined a light on the board?
Would it work if I shined a light on the board? Maybe. Maybe. I don't have a light handy to try it right now. Although I could probably, there are probably some lights up here we could do. I should have played around with this earlier, but no. Oh, maybe? Well, no. Maybe this one? No. Well, anyway, house lights? I don't know. Well, I'll try to figure it out. We'll see. OK, today's lecture, we're going to talk about stacks. Now, who has dealt with stacks before in some other class? Raise your hand. For about a quarter of you, maybe. OK, great. This is new for a lot of you. Woohoo. Right? Most of you guys have seen linked lists before. Now, this stuff a lot of it's new. You may have heard of the stack in terms of computer memory for a program having a stack and a heap. We're only going to briefly touch on that version of a stack. Well, we're going to spend a little bit of time on it. But as far as we're concerned, there is an abstract data type called a stack, which actually is modeled by this diagram on the screen here. It's boxes that you can pile things into one at a time, and the pile gets higher and higher, and you can only take one off the top. You can't dig down below and grab the one below. So that's kind of the idea. We'll get into that as we go along here. OK? All right. We're going to talk a little bit about yesterday's lab. In fact, I'm going to once again show you debugging, how I might debug using the Eclipse debugger. Because yesterday when I was in lab with with a few classes, a lot of people got stuck where their program just terminated or it didn't print out the right output. And they kind of were like, I'm not exactly sure where to go from here. Like, I don't know exactly what I should be doing. And they wanted to go down the cout route and error. And you can do that, like actually print messages to the screen. That's fine. But using the debugger tends to be a little bit easier once you get used to it. So I'm going to show you that a little bit too. Now, second thing, for those of you who found yesterday's lab a little tricky, part of it could have been a time thing. Like you just got into the lab and you hadn't seen the actual code yet, and it was a little bit tricky. But remember, linked lists are all about bookkeeping and all about making sure you know what the situations possible are. Are you at the head? Are you at the tail? Is there something special about those? And then when you are actually changing something about the linked lists, making sure that you make the right pointer changes in the right order. OK, does that make sense? I mean, that was what yesterday's lab was all about. You will find the exact same issues, except that it's a singly linked list for the homework assignment this week. So get started on that homework assignment early, specifically because it's going to be harder, and there takes longer to debug. OK, questions on that one? OK, we're going to do this stuff. Stacks is going to come down a little bit. Unix tip of the day. First thing I want to show you are two programs. One is called DC, and the other is called BC. OK, first things first. Let me go on to Tufts. We're going to look at the BC program. Now, this happens to be a calculator. Right? So I don't know if you knew there's an actual calculator built into Unix. And it's been around since the late 60s or early 70s or whenever Unix started. Right? And you can do things like 12 times 5. And it prints out 60, which is appropriate, I think. All right? And then you can chain things. You can do 12 times 5 plus 4, 64, et cetera. Let's see if parentheses work. 12 plus 4 times 5 gives you 80. like that. Okay, so it's just a calculator. The cool thing about this calculator is that it will actually do precision as much as you want, which is kind of neat. 2 raised to the 10,000. That's going to be a pretty big number, correct? Boing. There's the number. Now, right? Right? You can do that. You can do, let me close this clear, and then run BC again, and then do 2 to the 100,000. Right? Boom. It does it just like that, right? This is really long, right? 2 to 100,000 is a really big number, right? And this thing will actually calculate that for you, which is kind of neat, you know, when it comes down to it. I'm actually just trying to copy it right now so we can get a, there's another program called Word Count, WC, and if you paste something into Word Count, it will actually count all the characters, letters, etc. And this one says there's 30,988 characters, or individual digits, in 2 to the 100,000. Pretty big number, right? So that's what BC will do for you, right? It also does things like square root of 2, although square root of 2 is not 1 in this case. What you have to do is you have to do BC, I believe it's -L, and then if we do square root of 2, it will give you, yeah, it'll give you like 20 digits of precision. You can actually say scale equals like 1,000, and then the square root of 2 will give you 1,000 digits of precision, right? Which is kind of neat. You can do all this stuff, like calculating pi. Who wants to calculate pi out to, you know, whatever? Actually, I'm not sure it has a pi function in here, but there might be. There might be. I don't think there is. Pi. I don't think there is a pi function. Yeah. But you could do that, right? You could calculate it to any distance. So it's pretty cool. Interesting calculator. Now, let me show you another calculator called DC. Now, as it turns out, DC came before BC, right? DC was desk calculator, I believe it stood for. Okay, and let me start typing some things in here. Okay, here's what I'm going to type. I'm going to type 4, 5 plus. And then I'm going to take P for tell me the answer. And it says 9. Interesting, right? If I type 4, 5, 6 plus times, right, it actually types 44. Right? If I do 4, 5 plus 6 times, any ideas what that's going to print out? Any ideas what that might print? What do you think? 4 times 5 plus 6, so that would be 44. Any other guesses? Yeah, Ben?
54.
54. How would you get 54?
Well, 4, 5 plus, I take that to be 4 plus 5 is 9. 9 times 6, 54.
I like that answer, right? So this is a totally different way of calculating some of these things, right? I mean, we can chain these things along as much as you want. 4, 3 times 6, 7 plus times, and it will print out like 156, right? What did it do in this case? Well, first it did the 6 plus the 7, right? And oh, there might be one other number. I might have forgotten one other number. I might have done one extra number in this one. First it did the 6, right, it did the 6 plus the 7. Yeah, I missed one number in this, so it's actually not quite a statement that I want. But let's see if I print out there. Yeah, it's still 156. Let's try it again. 4, 3 times 6, 7, 5 plus times P. Yeah, there we go. So what this did this time is it print, although that doesn't look right either. Well, I don't know. Well, I'll show you what this is actually talking about in a little bit. But this is a different way of calculating. And what it turns out is BC actually uses DC to do its calculations, or at least it used to. And so we'll find out why that might be the case. Okay? All right, when we go into a little more detail a little bit later. But anyway, that's what I want to show you for as far as the DC and the BC programs go. Okay, nice little calculators you have available to you on Unix. All right, Eclipse tip of the day. So we're going to do a little bit more debugging right now. What I'm going to do, hopefully this will work. SSH-X. Actually, I'll just do it my special way. There we go. I have a little function that calls this, and there we go. I have a feeling that I might still have it running in the other office, so let's see. Yep, I thought so. So here's what we do. We do /comp/15/public files kill Eclipse terminated. All right. And then now we should run it again. Hopefully nothing got destroyed when I did that. And there we go. Ooh. Uh-oh. Might not have killed it yet. Hang on. I may not be able to do this. Hold on. May have to pause on showing you this.
I've done it a couple times. I actually have to go in and delete the .lock file.
Oh, the .lock file?
Yeah.
Star.lock. Is it in the
It's in the metadata directory usually.
in the Eclipse metadata directory? No, workspace.
I'm trying
Thank you for letting me know. We will. I don't see it here. Hang on.
Oh, wait, not log or not log?
lock.
Lock.
Oh, it's LCK.
Oh, LCK. Star.lck. Nope. Let's see. Here's what we're going to do.
I posted on Piazza a while ago, like how to
Did you post it on Piazza? That's all right. I will recover. Hold on a sec. Temp / student lab to SCP. Here's what I'm going to do. CD Dropbox Tufts temp make directory student lab 2. See how quickly I can do this. Ready? SCP *2. That's not going to work. Hold on. Hold on. CD student lab 2. Oops. Lab 2. SCP from my folder at Linux. Oops. .cs.tufts.edu. I know this is riveting, isn't it? Okay. Temp / student lab 2 / star to here. Cross your fingers. Good. Okay. Let's run it. It's all right. Run Eclipse is already running. We'll do it here. Forget that, please. Okay. Hold on. All right. Hold on. Close project. The best laid plans, right? All right. Project. Close project. You should always close the projects you're not working on. Didn't tell everybody that, but sometimes if you don't have the projects closed, it tends to screw up some of the issues. Student lab 2, empty project, good, advanced settings. Everybody says, hey, we have to do this each time. Well, look how easy it is. It's not that hard. All right. I know. It's a little bit of work. Hold on. There we go. And then temp, student lab 2, open, OK, apply, C++ build, settings. There we go.
Way to set that as the default.
Say again?
There's no way to set the command.
I don't think there's a way to set this as a default, actually. I've been trying to play around with that. If I figure it out, I'll let you know. If you figure it out, let me know. OK, done. Now, OK, this is where I wanted to be 2 minutes ago. All right, so we go and here's the student's program. We're going to try to build it. Oops, whoa. We're going to try to build it here. And it says nothing to build. Hold on. Build. OK. Don't do this. Hold on. Hang on. Build. Project. Clean. Hang on. If this doesn't work, I'll give up. It's not going to work. Hold on. Project, clean, build, all not working. Run, configure project. Run, configurations. That's the issue. Search project. Hey, say again.
When you were setting it up, did you change 3 things to?
I only changed 2, but I think I only needed to change 2. Maybe I didn't. Hang on. We'll check one more time. We'll see. This one, maybe I didn't apply it or something.
I don't think you changed the.
No, I didn't change this one, but I don't think I need to.
I don't think I don't think you did the second time we have to do Clang++.
This one I did, and this one I did.
Oh, I guess.
I did. All right, hold on. OK, well, this will have to wait till next time, because I can't figure out right now how to do it. So I apologize about that. All right, you make it out a little early, too, which is nice. Bottom line on debugging is that if you use the debugger, you can go, I've showed you this before, you can go in and you can see exactly what the state of your, in this case, your linked list is. And you can say, hey, if I'm inserting Charlie Brown into the linked list and Snoopy is already there. I need to put Charlie Brown after Snoopy because Snoopy's time is before, etc. You can see that happening in the actual debugging when you're going through this. So that's the nice part about the debugging. OK, sorry about that. Homework 2, you will probably have lots of opportunities to debug. Why? Because linked lists are tricky, right? So you have to do that. Same thing as before as far as the homework goes providing. You will get all the tests we used. If you do provide and the test fails, you should use that for your own testing. I've already got one of the TAs working on doing more tests that you won't get, corner cases that you should be testing on your own, like inserting into the head of a list, inserting into the tail of a list, etc. OK, that makes sense? You're going to have to do some of those tests. It's not going to be provide, test passed, you get 100. Not going to be quite that easy this time. All right, sorry about that. Let's go on to stacks. OK, so as I said right at the beginning, a stack is an abstract data type. Now, what that means is that, remember, we've got a kind of a differentiation between a data structure and an abstract data type. An abstract data type says, here are some functions I want you to do. And the data structure is the underlying method for doing it. Are you using a linked list? Are you using a dynamic array? OK? A stack we can build with either a linked list or a dynamic array, or probably some other types of data structures that you can. There's lots of different data structures you might want to consider for a stack. But in this case, and today we'll talk mostly about doing it with a dynamic array, just because it's a little easier to do. Let me pull the screen up a little bit here. OK. All right. And there are 3 things you can do according to this abstract data type. OK. You can push onto the stack. OK. What that means is you can place an entity onto the top of the stack. Now, we're going to model stacks kind of up and down. You can model them using an array from left to right as well. We're going to model them up and down because that's normally the way we conceptually think of them. But what I'm going to do is I'm going to just do it like this. Think of this as an array tipped on its side, where there's some memory addresses here. And depending on how your stack is oriented, the memory addresses may get bigger or smaller. It doesn't actually matter. The whole point is, when you push something onto a stack, let's say we push the number 7 onto the stack, it's going to go down there into the first location in the stack. And then we're going to push like 4 onto the stack. And if we push 4 onto the stack, it's going to come above 7. And that's kind of the thing. Think of anything that's stacked up, pennies or pancakes or whatever, right? It's going to be, we're going to stack it on. If I pushed 9 onto the stack, whoop, it goes right onto the top of the stack there like that. OK? This is actually called the top of the stack. The last one that you put in is the top of the stack. OK, that's how the model goes. This is a little bit out of order in this case, but this is called the top here. OK, all right. That's one thing we can do is push onto the stack. We can also pop off the stack. OK, and by popping off the stack, what we mean is taking the top value off. And that's the only one you can access. According to the stack abstract data type, you can't do anything but grab the top one. Even though 4 and 7 are in here, if you start trying to say, I want these ones, you're not a stack anymore. Fair enough? OK, there's very good reasons why we do this. But push onto the stack goes in order. And then popping off, the first one we pop off would be 9. The top now is going to be where? 4, yeah, because the top actually is the last one that's in the stack, the topmost one. Okay, they were nice enough to name these things pretty easily, like as far as understanding them. Okay, and then you can actually, there's another function called top, which says, peek at this one, tell me what it is, but don't take it off the top. Okay, that's not necessarily required, but almost all stack implementations, well, most stack implementations will allow you to just kind of peek at the top, but not take it off. Okay? The 3 big things. There are also some more things in there. For instance, there's an isEmpty function you might want to call. IsEmpty would be if the top of the stack had nothing, like if there wasn't anything there, right? That would mean isEmpty would be true, because there's nothing on the stack. Okay, so you might want to implement an isEmpty function as well. Okay, and there's some other functions, like you could have a function that's makeEmpty, which means pop everything off until it's empty, something like that. But in general, these are the three things we want to do with a stack. Okay, fair enough? All right. That's all we can do. But what and because only the top one is available, right? Only the top one is available to us. This has an interesting pattern to it. Okay? Stack-based operations are called last in, first out. And you might have heard this in other disciplines before or other things. But basically it means if you're the last thing onto a stack, you're the first thing off of the stack. Okay? So in this case, the 4 was the last one on the stack. Goes 7, 9, 4. 4 is the last one onto the stack. And therefore, it's going to be the first one off. Right? We put 7, then 9, then 4. 4 we pop. That's going to be the first one. 9 we pop. That's going to be the second one. This is a pattern. And this is a very typical pattern that you'll see in a lot of different ways we access data, as it turns out. Okay, as it turns out, you will see this last in, first out. There are other models. There's a first in, first out, which we'll talk about when we get to things called queues, right? Would a first in, last out be any different than last in, first out? No, I think that's the same, right? First in, last out. The first one in, if we put 7, then we put 9, then we put 4, the first one in is the last one out. So that's really the same thing. We normally call it last in, first out. It doesn't matter. Okay? Yes, question?
There is a difference in semantics that could be implied there.
What would the difference be?
Anything other than the first one in didn't matter the order.
OK, but this is strictly ordered. Like if you're no matter what the state is, last one in, first one out, and you can't reorder anything.
Yeah, but if you called it first in, last out, then anything that wasn't first.
But why can't I do the same thing here? Wouldn't the semantics for this be the same? Last in, first out?
No,
same?
Because you're specifying exactly the last one.
Oh, OK. All right. Well, anyway, I guess I see what you mean. Semantic issue.
And then once you remove that, the next one is the last one.
OK, fair enough. Fair enough. But it is the first one is the one you're dealing with, or the top one is the one you're dealing with. OK, I'll buy that. We're going to call it LIFO. All right, last in, first out in this case. OK? All right. So even though there's these limitations, right? Even though we're totally limiting you to what you can do with the stack, OK? What this enables us to do is model a lot of different types of things that we like to do in either data structures or other types of algorithms, right? And you may not be able to think of some off the top of your head. I'm going to show you a couple examples today that will be very specific about that. Okay? Stacks are actually so important in computer science in general, right, that they are built in to like the lowest level of architecture in terms of the instruction set. Remember the other day I showed you a bunch of assembly code, and I said, this is kind of ugly, makes your eyes bleed. Well, some of those functions there were almost certainly pushes and pops. And that's because at the machine code level, there are these operations called push and pop, which take basic data and move them into memory in this stack-based model. Okay, so that's kind of cool. I mean, the stack has like a lot of uses at a very core level. Yes?
Does the stack know how many is in the stack, or is that up to outside?
Good question. Does the stack know how many is in the stack? You, in general, would want to keep track of that because you probably want to know you probably want to say, hey, how do I know if I'm empty or not by keeping a list of how many are in there,
Oh, so
right?
it doesn't even
That's
know when it's empty.
well, you have to if you want to write an isEmpty function, you should keep track of how many items are in it. Now, that doesn't mean you can get to any of them randomly, of course, but you probably would want to keep that there. Yeah.
In at least a dynamic array implementation, isn't top the same as or one less than how big it is?
Yeah, exactly. In a dynamic. So well, in a dynamic array, it would know implicitly because we're using a dynamic array. Yes, but the stack ADT doesn't really know unless you implement isEmpty. I mean, as far as the abstract part of it. But yeah, this is absolutely true. If we're implementing a stack as an array left to right, okay, well, we start putting elements in here. right? This is now the top. And you're right, if there's 4 in here, top happens to be at position 3. And so you know that there's, if you know that if you know how many are in there, then that's, because it's a dynamic array, you're going to keep track of that. For an array, or for a linked list, that's not necessarily true because, like for your homework, I purposely left out the idea of how many items are in the linked list. You can keep track of that, though, if you want to. Like you could. But yeah, that's absolutely right. By a dynamic array, you're going to know, by using a dynamic array, how many are in there to tell whether or not it's empty. OK? All right, so turns out that even, and going one level further than like, hey, it's at the bottom of our, it's at the most basic level of our architecture, right? Some of you may have heard in a PC program, you are dealing with the stack, right? And I'm putting in quotes because the stack exists for every program you run in general. It has its own section of memory that is modeled as a stack, and that's part of the program. And you don't, generally in C, you don't explicitly like do things with the stack. But when you make a variable, that like if you do something in your function, right? If you have a function, right? If you have a function like this, and down here somewhere you say int a, right? Well, int a actually gets put, the a gets put on the stack, meaning in this region of memory that's based on the stack model. Now, it's definitely more. You can do more with that stack. You can actually reference it directly because it is memory, and they don't want to be limited to like only the top and bottom. But in terms of where it goes on the stack. So the stack model is, again, very fundamental to computer programming in general. Okay? One thing that's kind of cool is that the stack memory block that is actually used to store the memory also stores when you call a function. I'm going to show you an example in a second. When you call a function, in other words, you're in your function 1 here, and you call function 2, right? Like you call function 2 from function 1. Everything that's happening in function 1, all of the what we call state, all the variables and everything actually gets put on the stack for safekeeping while you're in the other function. Okay, that's actually what's going on. You've got to, when you call another function, the compiler has to say, oh, when it's compiling, it has to set all this up. It has to say, oh, at this point, save everything that's currently going on so that we can get it later, and then call this function. Because when you call a function, you don't want to have to worry about what the other function that called you was doing. You don't want to set that stuff up, right? You don't want to have to. You don't want to have to do that. And it purposely does that, and it's a stack-based model, and I'll show you why. Okay, here's 3 functions. Okay, let's say we have 3 functions. We have a main function. Okay, and the main function calls function 1, and function 1 calls function 2, and function 2 calls this other function 3, which I actually haven't put on the screen. Okay, so function 1 main calls function 1, function 1 calls function 2 calls function 3, and every single time we have to save the state of the function we're in before we call function 1. So first we save the main stuff, whatever's going on there. When we're in function 1 and we call function 2, we have to save all the stuff in function 1. We've already saved the stuff in the main. When we get to function 2, we save the function, or when we call function 3, we save function 2, etc. Does that seem like a pattern that we might have just talked about?
Yes.
In what sense? Yeah.
Well, when you're, you're putting things in the stack
Yeah.
in a specific order, and then when you return from functions, you're going to be returning to them in the reverse of the order that you put them in.
Exactly, and that's a key idea. When function 3, somewhere that's not written here, returns, where in the function 2 does it go to? When I call function 3, where's the next line that it goes to in function 2 when function 3 returns? The return here, right? So function 3 happens. All that stuff we just stored, we have to restore so that now we're in function 2 again and everything's back to normal. Because you certainly don't want the next program to be screwing up, or the next function to be screwing up the stuff that you worked on. That's why you save it. Yeah, Alex.
Is this why recursive functions will often like mess up your stack and like overflow, because as you keep coming back up through returns, it like kept dumping the function on the stack over and over?
Yes. Now, what Alex just talked about was this idea of recursive functions. Did you guys do recursion in Comp 11?
Yes.
You did. OK, so you guys good. Well, when we do recursion again on you what? It wasn't good. Oh no. It was great. It wasn't as thorough. Well, we will do a more thorough treatment of recursion. But yes, so to answer your question, Alex, yes, when you're doing recursion, every time you call a function, and remember, recursion is basically, if you don't know, that's OK. Recursion is basically calling yourself. Like, it would be as if function 1 called function 1 instead of function 2. And it's a very cool pattern. But what happens is every time the function gets called, you have to save the state on the stack. And if you do it too many times, it will crash, because the stack only has a certain amount of memory assigned to it. Okay, you can change that to some extent, but you may only be able to call your function 10 or 100 or 1,000 times before your section of the stack says, I'm done. I can't do it anymore. So recursion is a very good pattern, but you have to be very careful that you don't get into this idea of doing a stack overflow, as it turns out. Okay. All right. So anyway, this is the situation up here. Okay, it looks like this. And what happens, and this is exactly what, I forget your name again, sorry. Aaron. This is what Aaron was saying, right? You save each state, and then after you get to the last one, you return in the opposite order. It's exactly a stack-based, from the abstract data type model, right? Okay, this is a last in, first out pattern. Main calls function 1, calls function 2, calls function 3. Function 3 is the first thing that returns. Function 2, function 1. That is absolutely a last in, first out situation. Okay, that's how it works. And here's how it looks on the actual in the actual stack, right? When you call main, well, I guess it's really when you call main and you then call function 1. Main gets, the stuff that's in main gets stored on the stack. Okay? Then you call function 1, or you call function 2 from function 1. Function 1 gets stored on the stack. And you just push it onto the stack. Same thing happens, and you can see the pattern here, right? Function 2, then function 3. And then when function 3 is done, it gets removed from the stack to well, actually, this would be function 3 calling function 4, I suppose. But when function 3 returns, it gets restored. The state of function 2 gets restored. And then the state of function 2, when it returns, its state gets restored. And then function 1, same thing. And then we're finally back to main. Last in, first out. Question?
So when you say that you're storing the state of a function,
Yeah.
is like, for example, is every variable in a function being stored in like an array in the stack, or?
Generally, yes. Now, it's not. It's in a certain sense, it's an array in the stack. But the way it kind of happens, and it's I'm saying save the state, but there's definitely some parts of the state that get saved. But if you do something like this, if you have function 1, right, and you have int a equals 3, right, and then you call function 2, and function 2, in function 2, you say int a equals 4. Right? And then you return. Right? What should the value of a be when you get back here?
Still 3.
Should still be 3, right? Because it has to store this value here. And now, it's a little more subtle than that. Like the names of the variables really doesn't matter. But it's basically doing that. It's saying anything that's variables here gets saved in the stack somewhere so that it won't get overwritten by whatever this one does. So when this one returns, you'll be back to where you started. You still want over here a to equal 3. You don't want it to be equal to 4 over here. Okay, so it's, like I said, it's a little more subtle than that, but that's basically the idea. Right.
So how would it account for, like, if you have int a equals 3, and then in function 2 you passed in a, changed the value, and returned it? How does it know not to write over that a with back to 3?
Well, be careful there. If we said function 2 a,
Okay, I was assuming a is like it has access to a. So it's like a
so So if it's a pointer, different question, right? Okay. This, if you said, if it was a pointer to A, right, and this doesn't make sense, but it's a pointer to A, and then you say, somewhere else you say star A equals 3. And then you pass in the address of A, or I guess it would just be, in this case, if it's a pointer, you would just pass in A. OK. Well, remember, you've got two ideas here. A is a place in memory which needs to get stored. Like the variable A needs to get stored somewhere in memory. If it's a pointer, it's going to have an address in there that points to some other piece of memory. Okay? And this one is what you're going to be able to change. By accessing it in this way, you're going to be able to change this, not this. This is what gets stored, yeah. The variable A gets stored. And then whatever if you have access to what it's pointing at, right, because this points to some address here. If you have access to this, sure, you can change that all you want. But in general, this is going to be on a different, this is not going to be on the stack. This is going to be in what's called the heap, which is a different place in memory, actually, as it turns out. OK, so there's, not always, but most of the time it's like that, OK? Yeah?
Since there's a low-level stack built into like the program as it runs,
Yeah.
Are we going to be, when we implement the stack, are we going to be like manipulating that in C++, or will we like be making our own stack?
Good question. We will be making our own stacks based on a dynamic array or a linked list or whatever you want. Yeah. You will do a lot of stuff with stacks in Comp 40 if you take Comp 40. OK, you'll be doing that. Charlie?
With the implementations of the stacks that we make,
Mm-hmm.
it's possible to privatize elements within the stack such that, because if you have a dynamic array, you could easily just
Sure.
break it by adding it. Can we make it such that it would crash it, or I don't know, say no?
Well, in a little bit, we're going to get to actually showing you what the implementation is. But if you don't, if you have a stack and all you have access to is push, pop, top, and is empty, there's no other way that the outside programmer who gets that stack can influence the inside part, right? Now, as the programmer, yeah, all bets are off. I mean, like as the one writing the stack implementation, sure, all bets are off, right? I mean, you can screw up the code so that it does that, but you have no, but you don't have to worry about that if your implementation is correct. Okay, yeah, very good question, but it's all about abstracting away the ability to touch anything below the top of the stack. Yeah, good question, very good question. OK. All right. So as I said, we can modify our dynamic array, or really we don't have to do anything to our dynamic array to make it a stack, right? We just have to say limit it to a certain functions, right? And those functions are pretty simple, right? Where should we insert and remove in a dynamic array for the best performance? Because we could insert at the beginning or at the end. For the best performance, and what would that performance be? Think about that question here while I erase the board. By the way, do you guys know you should always erase up and down instead of side to side? You know why? It's so your butt doesn't jiggle. Side to side. You guys thought it had to do with like, some the grains in the board or something. No. OK, so all right. When you catch me going side to side, you'll laugh. All right, so here's our dynamic array. Typical dynamic array going from like lowest memory on the left to highest memory on the right. Okay, where do we want to insert in here for our stack? The beginning or the end? Let me just write down 4, 2, 3 in there. Where's the top going to be, and where should we put it? Yeah. Insert at the end. Why? Sure. Linear behavior? Oh, that's well. So I insert at the end. I put 9 in here at the end. OK. And did I have to move anything? No, and that's probably your point, right? That you don't have to actually do the moving. If I tried to insert here, well, I have to move 4, move 2, move 3. That's a pain, and that would be what kind of behavior? Linear, because I'd have to go through each one and move them, right? Remember, with a dynamic array, you have access to the last element. I mean, you also have access to any of them, but you certainly have access to the last one. And if the last one is empty and you can put it there, you put it there, right? So we definitely want to do it at the end. And what is the asymptotic behavior? It's not linear, close. It's constant, right? Order 1 behavior. Why is it order 1? Do we care how many other elements are on the stack? As far as we're concerned, for a dynamic array, right? Inserting at the end of this, if inserting at the end is inserting at the quote top for our stack model, and if we're inserting at the end, all we need to do is put it at the end. How about pop? What's the complexity for pop in a stack for a dynamic array? Also constant. Isn't that the holy grail of what we're looking for? Ah, that's very nice. Okay, so beautiful, right? We've solved all the world's algorithm problems with using a stack. Hold that thought for a sec. In a linked list, where's the best performance? Where should we push and pop? In a, I don't care if it's single or doubly linked. Yeah?
Either the head or the tail if you have a tail.
Yeah, if you have a tail, you can do it at the tail, because if you have access to the tail, inserting is a constant operation, right? You need to change some pointers, but you have to go through all the linked lists if you have the one that you're starting at. No, the head's probably a better choice in general, because you always have a head. But if you happen to have a tail, sure, do it at the end. Doesn't actually matter, right? Doesn't matter. So again, for and this is exactly, it's like you read these ahead of time. It's exactly the same, right? You get constant behavior. Beautiful. Okay? Solved all the world's problems by doing that. Are there any downsides to using a stack? Hang on. Somebody has an answer in a little bit. Downsides to using a stack. What do you think, Logan? To find something. Yeah. If you want to find 4 in a stack, in this stack that's 4, 2, 3, 9, 9 being the top, how do you do it? Pop, 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 pop. You've lost the 9, you've lost the 3, you've lost the 2. I mean, you could pop them and push them into another stack, right? Which is actually something that, you could certainly do that. Have another stack and then reinsert them, right? But that would get ugly, right? So yeah, searching through a stack, not so fun. Okay, so that's certainly, right? I think that's actually one of my other bullets here. No searching, that was the last one. Okay, now you've seen the other ones. You don't have any random access here, right? Now, there are other, like a linked list, you don't have any random access. We already talked about that. Like, you can't go and say the 5th one. Now, in your homework assignment for this week, you will have to find the 5th one, because I'm still making you do an insert at index, right? But it's going to be painful. How do you find the 5th one? You have to walk the whole list to find that one, right? If I say insert at index 17, you have to go, okay, here's the head, count out 17, and then I insert it there. See how that works? So it's not so easy on the linked list, and I'm being mean by making you do that, because you'd almost never do that in a linked list. But I'm being mean. Okay, sorry. All right. So so no random access, and no walking through the stack at all, right? I mean, you can't access the 3rd one down unless you pop off and keep that somewhere. Just according to the stack ADT, you can't do that. All right. The benefits, so simple. Push pop top, is empty. That's that. Okay, very nice, clean interface for doing stuff. Okay, and another advantage is that it actually fits a lot of problems. I'm going to show you some in a couple minutes. Okay, all right. Here's an example of using a stack. Now, this is not a stack, right? Anyone know what this is from? From Lab 1, right? This is from Lab 1. This is not a stack. In fact, notice we haven't done any real coding yet for this, because stacks are actually pretty easy. I didn't want to waste your time doing all this code. We'll do a little bit at the end, but they're pretty easy to implement, as it turns out. We can come up with an algorithm that uses a stack to do the following: to determine if a program, like a C or C++ program, has properly matched bracket symbols. Okay, a couple of you guys have talked to me about you actually wrote Nathan, you told me you wrote something to do this before. I'm not sure if you used a stack or not. But you can do this operation where you say, hey, are all my parentheses appropriately placed in this program, right? And we can walk through this and we can see, you can look at it right now. I've made them on the screen. I've highlighted them here. But if parenthesis, open parenthesis temp equals null close parenthesis. Is that a proper pairing? Are there any other brackets or parentheses in the middle there that would screw it up? No. Okay, there's an open curly bracket. That open curly bracket is followed by some stuff and then a closed curly bracket. Same thing, nothing in between. Now, if somewhere in here we had an open parentheses and then no closed parentheses, that would be a mistake. Why? Because you can't have something that opens with a curly bracket, has an open parenthesis in there, closes the curly bracket, and then somewhere else closes the parentheses. See how that's, like, that would be incorrect syntax no matter what? Like, there's no way you can come up with this unless you have some other, like another curly bracket in there. Okay. And so we're going to be able to do this with a stack. Anybody want to try to walk me through the idea here? I will show you the official algorithm in a minute. But let's see if we can figure out what to do here. Here's my stack. Okay, I'm going to start with the stack. That's the first part of the algorithm. All right? Okay. What are we going to do for this program to kind of figure this out? Ideas? Yeah.
For every parenthesis or bracket or whatever, if it's an opening one, put it on top of the stack.
Okay, I like that. What are you going to do with the things that aren't either parentheses, like the curly brackets and the non-curly brackets? Ignore them, right? So that's the kind of the first thing. We go through the program and we say, all right, if it's not a bracket that we care about, ignore it, right? Read it in, the I, forget about it. F, forget about it. Space, forget about it. Open parenthesis, what do? Push it on the stack. So it's an open parenthesis, we push it on the stack like that. And now there's, the top of the stack is an open parenthesis. Okay, then what?
If you find a closing curly bracket, whatever,
Uh-huh.
and it matches the one at the top.
And it matches the one at the top. Okay, so what are we going to do? So how do we say, does it match the one at the top? There's two things we could do. We could either, well, an if state, okay, but how are we going to access? What I mean is, how are we going to access the top of the stack? Either top or pop. Which one makes more sense? Top makes more sense?
Because you might be not.
All we're trying to find out is if they match. If they don't match, we're going to say error, right? So which makes sense? What did you were shaking your head. Pop. Yeah, let's think about it. If you said top, it would peek at this one but leave it on the stack, right? Well, it's an extra function if you use top. I mean, you would say top, and then you'd go, oh, okay, pop, right? Now, unfortunately, I say unfortunately, one sec. Unfortunately, some of the later labs will use a queue and a stack. In C++, you actually pop does not give you the top of the stack. It just removes it and doesn't tell you what it was. I don't know why. I've never quite figured out exactly why. But so sometimes you do have to do top then pop to figure out what the actual value is. But that's all right. Yeah, question?
But we might want to leave it in place and add something to the next one.
You might. Would that make sense?
If it's
Yes.
Mm,
If it's a bracket or a brace.
if it's a bracket or a brace. Ah, very good point. Very good point. So if it's not the same symbol, you're going to want to just look at it and not do that. Yeah, very good. Okay, yes?
That's only if it's a left brace, though.
Well, yes.
If it's a right brace and it's not one of the things you've done.
Ah, there's the key. Did you see what he was talking about? So if you do top and you peek it, so let's say you're going along and you get a left curly brace, okay? And then you get somewhere along the line, you get a right parenthesis, and you just peek at the curly brace and you say, nope, they're different. What can you immediately say? Something's wrong, right? So yeah, so actually, the top part actually, you're still going to have to remove it, or you're still going to have to just fail anyway. So yeah, you never, if you get a right brace of any type, you want it to match. If it doesn't match, you're in trouble. That makes sense? Let's see if it works for this one. OK, so now we're getting there. Now we're getting there. We have said if left parenthesis temp equals null, we get to a right parenthesis, and we say if we get to a right parenthesis, we pop and check. So we pop the left parenthesis off, and we say, is it the opposite of the right parentheses. In our case, it is, so we can continue. Right, that's what we're going to do. We're going to say, so far so good. Okay, these guys we're not going to worry about anymore. They're done. All right, then we go and we get to the left, or the left curly brace. We push it on the stack, right? And I'm notoriously terrible at doing left curly braces. And then we go ahead, ignore, get a right curly brace, same exact pattern. It's a right brace, so we pop off the left and we check, and then they do match, so we're good to go. And we pop that off. Okay, I didn't get anything. It's the same exact thing for the parentheses here and parentheses. Now here's where it gets a little bit more intense. Okay, just a little though. We get to this left curly brace right before the temp bracket I. Get to this left curly brace. We push it on the stack. Okay, then the next thing we get to that we care about is this left square bracket. What do we do with that? Also push it because it's a left. Now we push that on the stack. Now, you can see that if things are nested, this stack could get pretty big here, right? But the next right bracket we need to see in this case is which one? It's got to be a right square bracket, because if it's not, then we know we've made a mistake. Well, we go along, we look, and we say, aha, there is a right square bracket. And so if we do that and we pop off the left square bracket, now we check it and it's a matching bracket, we're good to go. And then the same exact thing happens here, right? We push the left one on, then we get to the right one, we pop the left one off, check it, it is the same, we're good to go. And then finally we get to the last curly bracket, which is a closing curly bracket, or a right curly bracket. We've popped the stack, we see if they match, and it does, and then we're done reading our input. Are we done? Can we say, we're good to go? That we have solved the problem, and yes, we have a properly formatted program as far as brackets go. Can we say that? What if you hadn't what? Okay, if you don't have if at some point during this, let's say we had a right curly brace, we would have failed because they wouldn't have matched, and we would have said we failed. So we know we failed in that case. But my question is, we do all this and we get to the end of the last curly brace, we pop off the last stack symbol, we pop one off, we check it, and then we say we're good. Are we quite done yet? There's one other thing we haven't quite figured out yet. Yeah, is that what everyone else is going to say? You have to make sure the stack is empty, because it could have been that this could have been, let's say there could have been one extra parentheses on the end here, which we would have gotten to and pushed it on the stack, and then the program would have ended and we would have said, yeah, we're done. But we would not have been done, because there would still be something left on the stack. So that's the last thing we have to do. Yes?
Can your stack be filled with dead squirrels?
Can your stack, you mean can all these other pieces? Yeah, sure.
Well, I mean, like, say you start off the program and the thing before it that ran had filled it up with other random stuff. So you get to the bottom and it's not empty because there's still other randomness in there. Like, how would you make sure that what you're checking is?
Well, so you start out with a stack that's empty. So you know that it's got you say it's empty.
Oh, okay.
Right? You say it's empty. You say that the top of the stack is like one below here, and you say the number of items is 0. So it doesn't matter what's in here. And then you'll either replace them or not. And if you don't ever replace them, you'll never get to that position in the stack to actually check it, because the top will never be a place that has dead squirrels in it. So yes, the array, just like any other time, can be full of these dead squirrels. Right? It can be full of junk that we don't care about. But by your functions, you'll only be able to access the ones that are real for the stack. That's the difference. So to answer your question, yes, but you'll handle it. Yeah. Good question. Other questions on this? OK, good. That's it. So let's see. Did we get it right? Make an empty stack. Read the characters until the end of the file. Check. If the character is an opening symbol, push. If it's a closing symbol, and if the stack is empty, we didn't actually say this. Right? If the closing symbol in the stack is empty, we should probably have checked that, right? Because that could have happened. Let's say the first thing you see is a closing symbol. If you tried to pop an empty stack, you should get an error. So we did skip that one. Sorry, I forgot about that one. But does everybody get that? Don't want to check the first thing is a thing. It's kind of the alternate to the last thing. otherwise pop the stack. If the symbol popped is not a corresponding opening symbol, you got an error. And at the end of the file, if the stack is not empty, you've got another error. Yeah, Charles.
In the algorithm, I don't see the point of reporting an error when there's not a corresponding symbol, because it wouldn't pop correctly, and then you would have a full stack by the very end.
What do you mean a full stack?
Or a non-empty stack at the end. Because there would still be something in it because it didn't pop it up correctly.
Oh, well, okay, how about this? You've got a program that's 1 trillion lines long, right? And you want to report an error as soon as possible, right? So in that case, report the error when you know there's an error. And then we can definitely say that if it's a wrong brace, we know it's an error. Yeah. And that's one thing. And the other thing is you really don't want to, I mean, if possible, you don't want to fill your stack up. You want to keep it as few symbols on there as possible. But yeah, I see your point, but there's probably better ways. I mean, doing it this way makes sense. Questions on that? You see how this is a model for stack-based behavior? If you can come up with something that's last in, first out behavior, probably work all right with a stack. Right? Yeah?
When you pop something off the stack, where does it go?
It's returned by the pop function. So the pop function will be something like, if you're putting integers on your stack, right? Int pop, like that is your function. It's going to return the int to you, and you have to deal with it then. Yeah. Top will do the same thing, incidentally, right? Top is also going to be return an int, but it won't go through the motions of making the stack go down by one element. That's the difference there. While we're at it, what would the function declaration be for push? Void what? Push int p or value or whatever you want. Yep, like that, right? Because in that case, you're not returning any value. I suppose if you wanted to, you could return a value, a Boolean value that says whether it was successful. If for some reason you've got a limited stack, you could do that. And that would be kind of a more advanced stack. But in general, we're going to say, all right, we're going to expand an array if we can, and so forth. Okay? But that would be those are the three big ones. What's isEmpty going to return? Boolean, right? Bool is empty, parentheses, parentheses, like that. And that just checks and sees if your stack has any elements on it or not. OK, good. OK, so we already did this. Make the empty stack and do it. All right. If we have n characters in the program that we are trying to analyze, the program of the characters in a program file, what is the asymptotic complexity of this algorithm? How about giving me the worst case, which is the normal one we want? This isn't code anymore, but it's an actual algorithm. What's the asymptotic complexity of this? Yeah, Alex.
Just suggest linear.
Why linear?
Because you're not actually increasing, like, it's only increasing like with the number of opening brackets, not with opening brackets, closing opening.
Careful. The fact that we're using a stack here is irrelevant in the sense that we don't care about how big our stack grows. That's not the issue here. The issue here is if n is the number of characters we have to go through, right? How many times do we touch each character? Once, right? And if we touch each character once and there's n characters, isn't that by definition a linear algorithm? And it's a linear algorithm because our stack allows what kind of access for pushing and popping? Constant access, right? So that part doesn't matter. Like the fact that we have the stack that's doing its stack stuff, well, each time we push on the stack takes one operation. Going through each character takes one operation. So that's really just a linear algorithm if going through all the things. So this is kind of a cool thing. You can walk through the program once and in a linear fashion and determine whether or not you've got all these brackets. Right? There are other ways to do this idea, right? I mean, you could say, OK, I'm going to go through and I'm going to number all of the opening brackets. Then I'm going to go through again and I'm going to number all the closing brackets. And then I'm going to compare the numbers. I mean, you know, you could say, does one line up with one, or whatever you're going to do, right? You could somehow come up with that, and that would be a nonlinear algorithm. But this is a nice linear algorithm for going through and determining whether you're properly parenthesized. Kind of neat. Okay, kind of neat. Okay, read through the file once in this case. Okay, and we said linear is not too bad. All right, so way back at the beginning of the class, before I couldn't use Eclipse, we had this calculator I showed you, DC. I showed you BC as well, but first I showed you DC. Now, DC, turns out, that weird way of doing math that I pointed out has a name to it. It's actually called reverse Polish notation. There was a guy who was Polish who came up with Polish notation, which is the exact opposite, right? So they call this reverse Polish notation. It is also called postfix notation, okay? They're interchangeable terms. A lot of times you'll see RPN because that's what they used to call it when they built calculators that actually did this, okay? Like actual desktop calculators that did this. In fact, you can still buy them, I believe. This is kind of one of the examples that we changed, right? 3 plus 4 actually becomes 3, 4 plus. This is what you change it to, right? What happens is you put the operands, in other words, the numbers you're doing things to, first. Then you put the operator, like the plus, times, divide, minus, whatever, right? And you follow those operations, and then you can turn that into this. But this is how you actually do the calculation, right? So 4, 5, 6 plus times, okay? The 4 and the 5 are operands. There's numbers. 6, which is also an operand, is not an operator, so you don't actually do anything yet. You get to a plus, and the plus says, take the last 2 operands and do that function. 6 and 5, you add them together and you get 11. That 11 is kept in memory in place of the 5, 6 plus. So now it's going to be a 4 and an 11, and then you get a times, and then you do the times on the 4 and the 11. You get how that works? Right? So yeah, it sounds like what? Sounds like a stack. Thank you, Cam. Yeah, it sounds exactly like a stack, right? Because you're pushing numbers on, and then when you get to an operand, you're popping a couple off, doing something, and pushing the result back on, and it's just a stack. Yeah. Charlie.
What about things like exponents, or taking power, 4 to the power of 5, or?
I refuse to answer that question on the basis of it's too advanced. No, if you have a order of precedence, you can then, you do have to think of that to some extent. However, in that case, it's actually not too bad, right? I mean, if you had 2 raised to the 3rd power, it would be 2, 3, and then the power symbol, whatever that is, right? Same thing. As long as there's 2 operands, this works great. Once you get into more operands, it's a little trickier, but most things are 2. The unary minus, in other words, -4, is a little bit trickier. Because -4 means you're going to have to do 4 negative, and then it becomes -4, so it's a little bit trickier. But yeah, to answer your question, as long as there's 2, this works great for it, and you can generally figure out a pattern for most of the others. Okay? All right, so that's how we're going to do this, right? 4, 5, 6 plus star. Let's see, the first thing we did was the 5 and the 6 plus, that's 11, and then 11 and 4, 44, right? The values to 44. Because the plus acts on the previous 2 values, etc. When an operator is found, it acts on the previous 2, and that's the one that we're going to use in the next time around. Okay? Like Cam said, it sounds like a stack. It is a stack. Okay? Should I make you guys try to figure out the algorithm? It's actually not too bad. It's actually not too bad. In fact, well, we can figure it out, right? If our stack is here, and we have 4, 5, 6 plus times, okay, what are we going to do with the operands? Push, okay. So we're going to push an operand 4, then push a 5, then push a 6. When we get to an operator, what are we going to do? Pop how many in this case? 2. So the plus says pop 2, and then do that operation. So we're going to pop up the 6, pop up the 5, and do plus. So it's going to be 11. Then what do we do? Push the 11 on, and now the stack contains 4 and 11. And we've gotten to the plus so far. So then we read the times. What do we do with the times? Pop. So we pop the 2 of them, 11 and 4, and then we multiply them. And so that's going to be 44, and we have popped those two off. And then what do? Push again, right? Because we could be getting more stuff later, by the way. So we push again, and this becomes 44. And let's say we want to print it out. What's the print out? What's the remaining on the stack? The answer, right? We pop it or we do top, and that's the answer that we got, right? So it's exactly what the DC calculator was doing, right? Same sort of thing. Read all the input, push the numbers until you reach an operator. When you see an operator, pop, right? And then apply that operator, push that result back on the stack. And then when you're done with the input, or you just want the answer to the top of the top of the stack is the result so far. OK? Aha. OK? Let's do this one. All right. Let's do this one. I'm going to read 6, 5, 2, 3 plus 8 times plus 3 plus star. Whew. All right. Hopefully my stack's big enough for this. We'll make it bigger if we need to. All right. What am I going to start doing? Push 6. Then I'm going to push the 5. Then I'm going to push the 2. Then I'm going to push the 3. Then what am I going to do? I've hit a plus. So then the plus gets pop off the 3 and the 2 and do what to them? Add them. Pop off the 3, pop off the 2. Add 3 and 2. You get 5. Then what? Push the 5 back on. All right. Then we hit the 8. Push the 8 on. Then we hit the times. Pop off the 8 and the 5 and multiply them, and we get 40. And then push the 40, right? Then we get a plus. Pop off the 40 and the 5, and then add them. So we pop off the 40 and the 5, and we end up with 45. Then what do? Push 45, and then we do, and then we get the 3. Push the 3, and then we hit plus. Pop the 3 and the 45, add them. 48. What do? Push the 48, right? And then times. Pop the 48 and the 6. 48 times 6 is 8. 6 times 8 is 40. I was right. 8, 4, and then 288. OK? And then what do we do when we get the 288? Push it back on. We're done with our input. What's the answer? 288, right? OK? That in infix notation, which is the one you're used to using. One sec, Charlie. Infix notation looks like this, right? And you say, I know how to do that, right? The only reason you know how to do this is because your 7th grade teacher beat it into your head about order of operations, right? How much order of operations did we need to know for this? None, right? No order of operations. How many parentheses did we have to have up here? None. This is actually a very cool method for doing arithmetic. In fact, there's arguments that this should have been what people are regularly taught, right? None of this order of operations baloney, PEMDAS, and all that baloney you learn in like 5th grade, right? Yeah. Question, Charlie.
If you have more operands than operators, will it just repeat? So like, let's say you had one more element left on the stack. Would it just keep repeating the last operator?
No, it doesn't do anything. The top is the final result as far as it's concerned. Yeah, as far as it's concerned, the top. Yeah.
Well, that was my question too. So, like, does it get an error if you end up with 2 numbers?
Well, it doesn't get an error, but you might get the wrong thing. I mean, if we put a 7 after here, right? The next thing on the stack would be 7, and it'd be like, I'm just kind of waiting for more stuff. You let me know you let me know when you have something else to do, right? And the 7 is the last thing on there. So as far as the answer would be 7 if the 7 was what you pushed on there. Yeah, good. Okay. All right.
What if you have more operations than numbers?
If you have more operations than numbers, you may end up getting to an empty stack, and then it would have an error. Because then you'd be like, I don't know what to do. I mean, we could test that we could probably easily test that in DC, right? Are we disconnected now? Probably. There we go. DC, let's see, 4, 5 plus times P. Oh, see, it says stack empty. So there's kind of an error there, right? It's not going to, in this case, it's not going to fail, but it's going to say stack empty, I can't do anything, right? So that's what's happening there. OK, where were we here? There we go. OK, so this is actually a pretty cool representation, no parentheses. RPN, reverse Polish notation, is a great system for a simple calculator. Okay? And it turns out engineers like things that are pretty simple, and it turns out that It's easiest to program because it's just a stack, right? So turns out the first, what Wired magazine called the first desktop computer, scientific desktop computer, was actually a reverse Polish notation calculator that had the ability to do extra stuff like trigonometry and logarithmic and was programmable. So you could do stuff like have loops and things, and you could write recursive functions and whatever to do some cool math. HP, actually, Hewlett-Packard actually called this the scientific, or the desktop calculator. They were going to call it a computer, but back in 1968, computer meant something like the size of this room. And so they were like, well, if we call it a computer, people won't take it seriously. So let's call it a calculator. Even though really, it had a processor in there and can do some kind of fancy stuff. Now, it doesn't have an actual like keyboard. You're not going to like write your English paper on this, right? But it does do like kind of cool calculations. Of course, it also cost the equivalent of $34,000 today, right? So you were, if you had one of these, your company was doing pretty well in general, or you had to do it so that your business would actually succeed, right? You could get calculators. You can still buy RPN calculators. Let's see if this works. I actually use one sometime on this little widget up here is a desktop calculator, is a RPN calculator, 4, 5 plus. You can see, I don't know, the font's really small, but right, it's a desktop calculator. I think I did the other one before, the 288 there, the one I did before, right? So you can get these for your computer or for your, you can actually get one that's a desktop calculator. The first handheld calculators were also reverse Polish notation. Kind of neat. Okay? Oh boy. You can convert infix notation, which is the parenthesized version, to postfix. It's kind of ugly. I made the teacher mistake last year of trying to do an example of this in class. And it like led to me like just kind of scratching my head going, I have no idea where I am. I mean, like I was trying to follow this algorithm with like a huge long string of stuff and forget it. This font is small for a reason, so I don't want you to necessarily read it right now, right? Basically, you can use a stack to convert from the infix notation to the postfix notation if you follow that algorithm. And that's what BC does, which then sends its output to DC and says, go calculate this for me. Okay, it first does this, converts it to the postfix and does that. So you can use a stack to do both, as it turns out. Okay, the calculation part is easier with RPN, as it turns out. Okay, so let's see. There's also this thing called a prefix notation. That's what we call Polish notation that this guy invented. And that's where you have the operators first, then the operands. Okay, so you do times, minus, and then I don't exactly know when it actually gets to evaluate. But the first thing, this evaluates, so the 5 and the 6 get subtracted first, then you multiply by the 7. So it's a little more work to actually get it to get it done. You can still do it with a stack, but it's a little more work. Yeah.
Pushing the operators into the stack first.
I'm not sure on this one. I think you are. Yeah, I think in this case you have to push the operators instead of the numbers. I believe that's what happens here. Yeah, the other side. But anyway, we will re-look at some of these postfix, prefix, and infix ideas later when we talk about walking a tree. If you don't know what a tree is, that's okay. But walking a tree, a binary tree, you can do it in either post order, meaning you go there and then at the end print out the node you're at, pre-order, which means you print it, then you go to the next one, and then in order, which means as you get to a node, you print it out. So it will actually mimic the ideas here in a big way. Okay? All right. So that's that. Questions on stacks? No? All right. I'll see you guys Monday.